this is important, remember this, and a standard distribution of 1. The distribution shape will always be the same as the original distribution because we're not changing the distribution of the scores, we're just standardizing them. Okay, so let's do review problem 1. In the review problem 1, we want to create a new variable that measures the degree of success in a person's life. That makes up a lot of things make up success. So the variable combines education, number of years of education, how much money you're making in dollars, the time spent traveling per year in days, and the size of the family, number of children. All these things are possible measures of success. But how do we measure them? They're different. Well, in this example, it'll be particularly helpful to use the z-score transformation because all these things are different. So we want to go ahead and do the z-score transformation because the variables are measured in different units. Okay, education is in years, salaries in dollars, etc. Review problem 2 is also about it, and we'll actually do some computations here to help you remember. So it's about the IQ of all students in the classroom, and the IQ follows a normal distribution with a mean of 110 and a standard deviation, don't forget that's a small sigma, equals 10. So let's compute the z-scores for the following IQ scores: 80, 90, 100, and 120 and 130. Okay, do you remember how to do that? Well, let's go ahead and do the first one. 80 minus 110 divided by 10 is -3. And just step through the math here. Let me just clear this guy. And so we take 80 and we deduct or subtract 110, and we then divide that by 10, and we come up with -3. Okay, so there you go. And of course, I haven't divided by 10 is -3. So that's the first one. I'm going to move that off the screen. The second one is 90 divided or minus 110 divided by 10 equals -2, and the third one is 100 minus 110 divided by 10 equals -1. And these are the z-scores, and 120 minus 110 divided by 10 equals +1, and finally 130 minus 110 divided by 10 equals +2. So there you go. Good review on z-scores. In review 3, let's talk about a given population where the mean is 70 and the standard deviation is 3. Figure out the z-score for x equals 76. Come on, you know how to do it. Just like we just did. Okay, 76 minus 70. So this x score minus the mean divided by the standard deviation is +2. And review 4, in a given population, if the mean is 70 and the standard deviation is 12, what is the score for x equals 76? And what did we change it? We changed the standard deviation. So what's going to change? The numbers in the formula. So we take 76, which is the x score, and we deduct the mean. That's the same, but instead of dividing it by the number that we did in the last slide, we now divide it by the new standard deviation of 12, and we come up with a z-score of 0.5. That's right. Let's go on to review number 5. What are the 3 methods for assessing the degree of normality in a distribution? You remember? We talked about it last week. A graph is one. You can take a look at it. And the second one is the Kolmogorov-Smirnov test. And you remember that, Smirnov, just like the vodka. It's an easy way to remember that, or the Shapiro-Wilk test, and SPSS is going to do those babies for you. And the third one that we talked about is the distribution is going to be within the realm of -2 to +2, and we talked about that last week. Okay, number 6 is, how do we normalize a distribution that doesn't follow a normal distribution? All right, there are 2 ways to do it. The first is we use the log function in SPSS, and will remind me to show you how to do that at the end of this lecture. And the second is that we recode or exclude extreme values. If you recall, we talked about that last week on the Z-square lecture. Let's talk about the key concepts this week. This week we're talking about something called probability. Okay, and we are not going to talk about this stuff until next week, because I broke this up into a couple of different parts, but I just made the PowerPoint all one big PowerPoint. So let's talk about probability. What is it? Well, probability sounds really complicated, but we use it all the time. For a situation in which there are several different outcomes, the probability for any specific outcome is defined as a fraction or proportion of all the possible outcomes if the possible outcomes are identified as A, B, C, or D. Wow. No wonder why the textbook, they paid these guys a lot of money to write this textbook, because it's extremely complicated. It's not really that complicated, guys. Probability of A is the number of outcomes classified as A divided by the total number of possible outcomes. Let's do an example. All right, grab a deck of cards, okay? The probability, how many king of hearts are in the deck? 1, right? And how many cards are in the deck? 52. So you take 1, you divide it by 52, you come up with 1.9%. Okay, let's take aces. How many aces? There are 4 of them. Okay, so you take 52 cards in the deck, and they equal, and if you, what we're doing here is just reducing this, and we come up with 7.7%. So you got a 7.7% chance of grabbing an ace out of 52 cards. All right, so if you're playing poker, you got a 7.7% chance of being dealt an ace. There are 4 of them, whereas you got a 1.9% chance of being dealt a king of hearts. Spades, okay? How many spades are in the deck? There are 13 spades. There are 52 cards, so we take 13 and divide it by 52. We come up with a quarter. That's equal to 25%. So we got a 25% chance of being dealt a spade. Let's take another example. A coin got 2 sides, right? What are the probability? What is the probability of you getting heads? Well, you got 1 out of 2 possible outcomes, and so you take 1, you divide it by 2, you get 50%. That's pretty easy stuff, right? So although Graviter and Wallnow have desperately tried to confuse the hell out of us, it's not that hard. Okay, this is what probabilities are. Let's take a frequency distribution histogram for a population that consists of n equals 10 scores. Okay, here they are: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, and the shaded part is the portion of the whole population that corresponds to scores that are greater than 4. Okay, so here's 4. The ones that are greater there's 2 of them. Okay, so let's take a random sample of n equals 1 score. What's the probability of obtaining a score greater than 4? All right, just like the cards. Okay, the probability of x being greater than 4 equals the possible outcomes divided by the total outcomes. So the total outcomes, there's 10 of them. Okay, there's 10 scores, and just like there are 52 cards in a deck, and how many are greater than 4? There's 2 of them. They're shaded blue. So we take 2 divided by 10, or actually let's reduce it, and just do 1 divided by 5, and you got a 20% chance of pulling a score greater than 4. Pretty easy. Okay, you do this one. What is the probability of x being greater than less than 5? So go ahead and do that, and let me know what the answer is. I'm going to pop over to the next slide. Okay, so let's go to estimating the probability of event A occurring. Let's say we roll a dice, or two dice. What is the probability of obtaining a sum greater than 10? Well, the number of outcomes where the sum is greater than 10 and total number of outcomes. How many dice are there? All right, there's 2 dice. They each have 6 sides. So we know that 6 times 6 is 36, and there's 3 outcomes. You can roll a 5 and a 6 and a 5, or 2 6s. Okay, so there's 3 outcomes. So it's 3 divided by 36, and that is reduced to 1 divided by 12 equals 8.3%. So that's the percentage of what you could do there. Now, zero probability. What is that? If you have a jar with 10 red marbles, the probability of randomly selecting a black marble is, you can't do it, all right? It's 0 divided by 10. There's no black marbles in there, equals 0. This means that the event, randomly selecting a black marble out of the jar of red marbles, just can't occur. Question: is the opposite true? Does a probability of 0 mean that the event will never occur? What do you think? Give me a yell and let me know. Example: fish in the sea. Can you predict which specific fish you will catch? No, you can't. The probability is just too high. Simple versus conditional probability. I think I'm going to actually complete this in 15 minutes. So you only have one lecture this week. In simple probability, all outcomes are equally likely to occur. Example: drawing cards out of a deck and putting one card back in the deck once you drew it. Okay, do you get what I mean there? So whereas conditional probability means that I take the card out and don't put it back. It refers to probability of an event, but taking into account that another event already occurred. Example: I drew the cards out of a deck, but did not put the card back in the deck once we drew it. Or we roll the dice. What is the probability of obtaining a sum greater than 10 if you got a 6 on the first roll? Well, then you got to get 4. There's only, on the other dice, there's only so many numbers that are going to add up to 10. All right, so it's conditional. The formulas for simple probability: it's P A and B equals P A. You know what? This is just confusing. Let's just go over here and take a look at the examples. You roll the die twice. What's the probability of first obtaining a 3 and then a 5? Well, there you go. Let's plug the numbers into the formula. Okay, so it equals P3 and 5. 3 times P5, and the probability, if you step through it, is P3 and 5 equals P3 times P5. When we reduce it, it's 1 divided by 6 times 1 divided by 6 equals 1 divided by 36 equals 2.8%. That's simple probability, and that's what we've been doing here. So P3 and 5 equals 2.8%. Simple probability, another example. I'm running out of time. I'm going to stop and go to the next slide. Not the next slide, I'm sorry. I'm going to go to the next lecture.